Okay, then after Max, I will introduce the second topic for the workshops, which is called Condition Monitoring with Self-Powered Sensor Systems. Yesterday I already talked about the Internet of Things and the challenge we face, that we have currently more than 20 billion wireless IoT devices and 32 expected for 2030. Special part of the IoT is the industrial IoT, where we have machines, plants and processes which are connected to the internet and which are optimized regarding their efficiency, their productivity and their safety. An important part in the IoT is the ICT, so the information and communication technology. And the aim of that technology is to collect the data, to transmit the data and process the data, so that it can be used to control different kinds of objects, machineries, plants. I have some examples what this ICT is doing in the IoT. So for example, the ICT can monitor the consumption of every kind of machinery, of a pump, of a motor. The aim here is to save resources. Another example of IoT application is predicted maintenance. So for example, measuring the vibration of a roller bearing, measuring the temperature of a motor. Here the aim is to avoid failures and to increase the productivity. And the third example is stopping machines in the event of a fault. And here also the aim is to minimize or to prevent damage. So the IoT is actually, or the ICT is actually used for green. So we use the information and communication technology to improve the sustainability of the machine, of the plants, of the process. But the question we are posing in our project is, how sustainable is the ICT itself? How sustainable are these IoT sensors? My colleague Max already mentioned that a big part of the IoT system is the battery and the CO2 emissions connected with the battery. Here the technology energy harvesting comes into play. I already talked about yesterday. So energy harvesting is a technology which uses ambient energy to generate electrical power directly at the sensor, so that we can get rid of any cables for power supply, so that we can get rid of the batteries or even shrink the batteries or replace them completely, and that we use ambient energy, so alternative energy sources during the operation of the sensor. Of course, there are a lot of benefits. We have a wireless power supply, we have a low installation cost, we have maintenance-free systems because we do not have to replace or recharge the battery. We can reduce the costs. We have an unlimited standby or operation time. We can even use sensors in inaccessible locations. And of course, we also can use sensors in a higher temperature range because we do not have batteries. The basic architecture of an energy harvesting systems, you have seen that yesterday already. We have an energy transducer that might be a solar cell, a thermoelectric generator, a vibration harvester. We need some kind of power management electronics, and we also need some kind of energy storage devices, because these harvesting systems do not provide the typical pulse currents we are needing for the communication technology. And of course, these three components are then used to power a radio module, to power a sensor, and to power an actuator. There are several technologies already available which can be used for energy harvesting. So the most mature technology are actually solar cells. We will use solar cells in our workshop the next couple of days. Solar cells are most mature. You can buy them in different shapes and different sizes from different manufacturers. They only have one downside: they don't work in dirty or dark environments. Another option for energy harvesting are thermoelectric generators. They use heat differences on surfaces. Here we already have also commercial components available which we can buy off the shelf to build a couple of hundreds or a couple of thousand sensors. This is the second energy harvesting type we will use in our workshop the next couple of days. There are another options for energy harvesting systems, for example, vibration generators. They use vibrations or deformations, for example, on pumps, on motors, on engines, or any kind of structures. They need to be tuned typically to the exciting vibrating source. That's the downside. And there are also no plug-and-play modules available on the market. So if you're going to build 100,000 or 1 million sensors, you have no chance to buy these huge amount of energy harvesting generators. So this is the reason why they are not actually used in commercial products. Another option are RF harvesters. They use radio frequency waves. They need to be also tuned to the source, so to the radio frequency. Here the challenge is that the power of these radio waves is strongly limited by regulation, so you cannot generate very high amounts of power to harvest these with your sensors. And finally, another option or final option I like to mention here are acoustic harvesters. They actually use noise, so noise, for example, from machines, from vehicles, but even from the human body. There are also no professional implementations available, so only research. So in our workshop the next couple of days we just consider solar cells and thermoelectric generators, and we will show you, or I will show you today an example, and I ask you in the next couple of days to use that example to adapt it to other use cases. So the first important energy harvesting source I already mentioned are thermoelectric generators. They use a heat on a surface. The challenge here is that the cold side has to be cooled to maintain a thermal gradient. You can use different kinds of heat sinks or heat sources in the environment. Typical examples are machines, which gets hot during operation, engines, pipes, but also components for heating, ventilation, or cooling systems, or even the human body can be used as a heat source to generate electrical power. The challenge is that the voltage from these generators is typically proportional to the thermal gradient. So if you have only a small thermal gradient between your object and the environment, they generate only small voltage levels. So you need DC-DC converters to up-convert that voltage to, for example, 3 or 4 volts to charge a battery or capacitor. Yeah, this is one system we're going to have a look on later on. Here is one of our technology demonstrator, which you can also use in your work and just to scale it, to adapt it to other application. So this is a self-powered sensor Bluetech. The important thing I like to show you here that, of course, depending on the thermal gradient, you get more or less output power of such a harvesting device. So here, for example, we have a thermal gradient of 10 Kelvin, and from 10 Kelvin out of that device we get a power of around 0.8 milliwatts of power, and it is of course sufficient to power a wireless sensor, to measure sensor data, to transmit the data over a radio protocol. Here's another example which you can use then in your work to adapt it, to scale it. This is actually a wireless module which uses 5G communication. We have built that module either with a thermal power supply. There we use a thermal gradient of 13 Kelvin, a tech harvester in a size of 37 by 37 by 20 millimeters. And with the power from that harvester, we get enough energy to do a measurement once every 15 minutes and transmit the data over 5G once every hour. We also use as alternative a solar module in the size you can see here on the slide, and with this solar module under a typical outdoor light condition, you also get enough power to measure your sensor data once every 15 minutes and transmit it once every hour. So here's just an overview table which kind of where you get an idea how much power you can get from the typical harvesting generators which you can use in your work later on. And here's actually the overview of your workshop task for the next couple of days. So your task in our workshop topic will be research, design, and carbon footprint assessment of a self-powered sensor node. In the first step, you should just research and development applications for self-powered sensor nodes. So think about where they might be beneficial, what might be the benefits of the sensor node in a typical application. Then we ask you to evaluate the application based on feasibility, on effort for implementation, on the benefits and on the cost effectiveness. Furthermore, we ask you to develop the requirements of these sensors in a given application. So think about how often they should transmit the data, how far they should transmit the data, how many sensors you would need. Furthermore, then we ask you to dimension the sensor system. Here we give you information regarding the ICs, and we just ask you to dimension the power supply. So just adapt the thermal harvester, just adapt the solar cell to the given application. And finally, we ask you to make a simplified carbon footprint assessment. Here you can get example data from our sensor nodes and just scale them to the application you have chosen. And finally, you should develop a couple of approaches to improve the carbon footprint. So as far as you see what the single components and their carbon footprint is, think about how you could shrink the carbon footprint of the single components. For example, expose the system to more light, and then you can shrink the solar cell and you can improve the carbon footprint. Actually, here is an example which we did in the past, and for that one we also will provide you the data so you can work with that data adapted to other use cases. Actually, this is a wireless sensor for measuring water heat on electrical energy consumption, and here in the table you see the performance. So for example, we do a temperature measurement once every 16 seconds, a flow measurement once every 2 seconds, we transmit the data once every 15 minutes, and that all results in a power requirements for 400 microwatts. So here's the block diagram. Of course, here are the functional blocks of the system. You need a microcontroller, a transceiver, an antenna, and so on. And here you have 3 options for providing power to the sensor node. The one is the yellow one with the solar cell, the blue one with a thermoelectric generator, and of course the third option is with a simple battery. We evaluated the carbon footprint of these 3 options just to compare their carbon footprint. Here are some data to dimension the single components. So in our use case, we choose a 34 watt-hours battery so that we can achieve a lifetime of 10 years without any recharging or replacing the battery. Regarding the thermoelectric generator, we considered a temperature difference of 10 kelvins, a DC-DC converter efficiency of 60%. We choose a given heat sink, and regarding, depending on our measurements here, we generate an output power from a 10 Kelvin thermal difference of around 44 microwatts of power to supply the sensor node. Finally, some examples, dimension examples for the solar cell. Here we used a solar cell of an area of 36.5 square centimeter, and with a typical indoor light condition of 500 lux, you get an output power of around 1.2 milliwatts of power. Of course, you should consider that you do not have light 24 hours a day. So if you reduce that to the typical 8 hours light per day, then you get an output average power of 0.4 milliwatts of power. Okay, then we did, for our example here, a carbon footprint assessment. Actually, we considered only the carbon footprint of the single components during production, because actually during the lifetime of the sensor, we do not have a carbon footprint emission because these sensors get their energy from the environment. So they use alternative energy sources and they cover the coal power consumption during operation from the environment. So we have to just consider the carbon footprint during the production. Of course, we also use for our work the SPIRA LCA for Experts database, because we also want to be experts, and this is the reason why we have to use this database. So thanks, Sarah, for that hint. We use the integrated circuits as David introduced that to you based on their package size, and we did estimate the ratio between the packet size and the die size to estimate the size of the die of the chip. We worked with the mechanical components based on their mass. We considered a battery lithium cell, which we scaled by their capacity to adapt it to our use cases. And of course, we also scaled the solar cells by area. What we did not consider was the assembly of the overall system and the installation effort. So we only considered the production, and this is also the proposal for the workshop for the next couple of days. Here's actually the result from our example here. So we compared the battery version with the version powered by a TEG, compared with the version powered by a solar cell. And if you can see here, the most important finding is, of course, depending on the lifetime of 10 years and the typical operating condition, of course, the battery version has the highest carbon footprint. This is due to the large battery. So if we would consider not a 10 years lifetime, but only a 5 time or a 2 years lifetime, of course, then the battery size would be reduced, and then this relation would change. So it's always depending on how long your product is in use and how you have to dimension the battery compared to the energy harvesting system. But you can consider that in your workshop for your chosen use case. Okay, and finally, here are some equations. There's no need to read through them right now. We will provide you a paper where we have developed these equations. These equations just help you to scale the different power supply components, like the solar cells, scale them in area, like the battery, scale them with the required capacity, and then you see how that results in the change of the carbon footprint. Okay, and that's pretty much it. This is actually a timetable we developed for you that you get an idea on which day you should achieve which kind of results. So for the first day, we ask you to have the research of the application. So think about different application, think about what kind of application you want to focus on. And then for the first day, also evaluate the application based on their feasibility and their effort, their benefits, and their cost effectiveness. And then, of course, you should prioritize and select a kind of application where you want to focus on in smaller group. That should be potentially done tomorrow, that you think about the requirements which are needed in these application. So what kind of sensors you need, what kind of communication distance, what kind of transmission frequency, and so on. And then you should dimension the sensor. Of course, dimension it only regarding power supply, so solar cell, thermoelectric power, or battery supply. And then for Thursday, you should do a simple carbon footprint assessment. So think about the size of your power supply components, have a look at our example, and scale or use the scaling formula so that you get an idea of the carbon footprint of the power supply components of the application you choose. And finally, of course, think about how you could minimize this carbon footprint of the single components. Perhaps think about what about measuring data and not always transmitting data, but processing the data on the sensor node compared to sending it very often, so that you can reduce the power consumption, and in that case, reduce the components for the energy supply, and finally, improve the carbon footprint. Okay, this is a paper we will provide you with the other material for the workshop starting this afternoon, and I think that's pretty much it from my side. Do you have any questions so far? Yeah.
Are we going to have access to this presentation as well?
Yeah, we put it on the SharePoint. You get the presentation and the paper. We have a SharePoint, an own cloud SharePoint, where all the students can access, and you can download that material and work with it.
Okay, thank you.
You're welcome.
And we work on the tasks in the smaller groups, right?
Yes, yes.
each group has to choose its own topic then.
Its own application. That would be much more interesting than
Yeah.
if we have 3 times the same application. So we see this afternoon how much people we have in the group. Then we decide how we should choose the group. Perhaps it should be at least 3 persons in each group, and then you should think about application, and then we decide which group focus on which application finally.
All right, thanks.
Okay. Any more questions? If this is not the case, then thanks a lot. I hand over to my colleague Peter.